What's up, you guys? It's Peter, and today I want to cover a foundational tool that will help improve your visual effects. It's the dot product. Now, before we dive into Houdini, I want to go over a little bit understanding how it works and show you some resources where you can learn more. And then we can dive into Houdini. I'm going to explain how it works in there and then also show some practical examples. So let's dive into it. So first, let me move the webcam thingy again. There we go. So a couple of good resources that can help you are basically on Wikipedia. You can find information about the dot product. Now, as you will see, that there's quite a bit here in terms of the definition and then the algebraic definition as well as the geometric definition. And we are mostly interested in the geometric definition. So, we can kind of sort of see the main definition over here. A dot B equals the length of A times the length of B times the cosine of theta, which is the angle in between. Now, we'll talk a little bit more later on the arc cosine to compute the angle in between a little bit later. So don't worry too much about all of this stuff. Where else can you find some good information? Well, you can find good information on Khan Academy. It's probably one of my favorite websites to learn things about mathematics and physics and biology and all kinds of things, depending on where you're starting. Because this website starts really basic and then goes quite advanced. So you can basically hop into the kind of knowledge, where your level of math is at, and basically dive in and understand more about it. So next, let me sort of explain a little bit on how we are going to use it in Houdini. So I've made somewhat simplistic drawings over here in Krita, and I want to talk a little bit about how it works. So what we have here is sort of a trigonometric circle. And if we look at the annotation here, it starts at 1 and it goes over to 0 and it goes to -1. And that will become the range of the dot product. So what is the dot product? Well, in order to understand the dot product, we have to assume that we have two vectors in our scene. So we have over here the blue one, this could be the normal, this could be a vector A, and the green one, which is a target vector, an up vector. In our case, it could be vector B as well. But notice that they are not necessarily, initially at least, the same length of unit length. So we want to normalize these vectors, and it is going to be the result of one vector projected onto another vector. Now, what does that mean, right? Well, let's have a quick look. So basically, if I take this dark green vector and normalize it, right? So the light green vector is a normalized vector, then we'll see basically that the radius within this unit circle, it is going to lie on top of that boundary condition of that unit circle. Now, if we project the green vector onto the blue vector, we are basically going to get over here the projection, right? And we're going to get over here a little distance. And it's that distance, sort of that projection, right, of the green vector onto the blue vector, that is the dot product. Now, you might wonder, why is this useful to me? Why do I need this? Well, there's some really useful applications that we can do with this in the sense that if two vectors align, if they are perpendicular to each other, if they are opposite to one another, we can get that information and, for instance, cover objects with snow, or we can say, okay, this is the direction that the sun is facing, or maybe the side that the sun is facing is bleached and the other side is sort of, plain. So lots of useful things. We can also do things like field of view, control that. So, which point, if a point is facing a certain direction, which other points can it see? It's sort of like fuzzy logic in terms of like crowds and their field of view. So we can kind of use it for that as well. So now let's kind of have a look, for instance, how this works on the Houdini side. So here in Houdini, I've made a little example where one vector is basically projected onto another vector. So what I've got here is two vectors, and notice that they are currently not normalized. So we've got a system whereby I can kind of say, okay, I've got my blue vector, I've got my target vector, my green vector, and then here I'm projecting right onto, in our case, this is in the z-axis, but could have just been the x-axis. But in the z-axis, the reason why is because then we're already in Houdini's world. So basically, if we project our vector onto the z-axis right now, we can kind of see, okay, the dot value over here, the dot product is equal to 0.63. Now, there are some important cases here. What does it mean when the two vectors align with each other? Well, when they align with each other over here, right, they basically, the dot value is currently 1.1. Right, that's because this vector is a little bit longer. So I'm going to dive inside of my example and I'm going to normalize my vector. So here I've built in a little switch to normalize it. We'll go back up in a moment, right? So we'll talk more about that example in a moment. But so there are a couple of scenarios that are sort of important to understand. When the angle between the vector is 0, then the dot product will be 1. As our angle increases, right, so basically here we're now at about 45 degrees, we are dealing with 0.7, right, and as we approach 90 degrees, our dot value perpendicular falls to 0. Our angle is now 90 degrees. Now if we keep going, then the dot product over here is basically going to fall, right, up to -1. And this is at an angle of 180 degrees. Now notice something, as I go beyond 180 degrees in my angle, right, you would say, okay, this is 180 degrees, but what actually ends up happening, right, is it takes the shortest angle. So notice that, wait a second, shouldn't my angle be like, much larger than this? Well, yes and no. If we just go from what the dot product is, it is going to take the shortest angle to get there. So it is basically the cosine of the two vectors. So that basically means right now, if we look at it, it would be here, for instance, so this might be a little bit easier to visualize. It's the cosine between the adjacent, right, over here, this little bit is the adjacent, and then here is the hypotenuse, right? So the angle here, right, is represented by that cosine, assuming that the normals are normalized. So if they're not normalized, we would have to maybe normalize them first, or we would have to take their length into account. So in a moment, we will talk a little bit about the general equation. We can basically show it just briefly here. Let me just hide this layer and let's bring up the other one. So here. So this is the general equation. So as I was saying, we basically have A dot B and then the cosine theta, right? That's the angle in between, the length of your first vector A, the length of your second vector B. Now what happens when we actually simplify it, right? If we basically normalize A and B, well, then this becomes 1, this becomes 1, and it simplifies to A dot B equals cosine theta. Now the dot product over here, the way that it is represented is with a big dot. So notice here I've got a small dot that implies a multiplication, whereas a dot B implies the dot product. Now you have another operation, which is a cross product, and we'll talk about that in another video. But right now we're talking about the dot product. So a dot B, when we're dealing with normalized vectors, is the cosine of theta, the angle in between. So over here, I've basically represented, my A vector, my B vector, and then the dot product will be the cosine in between. I've already converted the angle to degrees. So the dot product can also serve the purpose of being able to extract the angle in between out of that. So that's also quite a useful sort of feature. So if we look at over here, how can we get to that? Well, how do you get rid of this cosine over here? Well, you do an operation called the arc cosine. So if we apply the arc cosine on A dot B and on the other side, then we basically are able to simplify this even further so that we get the theta. So theta is equal to the arc cosine of A dot B. Okay, so how do we compute that in Houdini? Well, let's have a look in Houdini now. So here is my, my example, and so the main scenarios here is the vectors are aligning, the vectors are perpendicular, right, and the dot product becomes 0, and then over here they are opposite of each other. And notice these values: -1, 0, and 1. So full opposite of each other is -1. When they are perpendicular to each other, it's 0, and then basically when they align, it's 1. And then we have all the values in between, right? So basically we can kind of sort of see as it does a full circle, and I just can keep rotating, and it computes for all kinds of vectors. It computes that dot product. Now currently this is in 2D, but this works just as well in 3D. So let's show how I've built this little example, and then what we can kind of do with this. And so here I've started out by building my first couple of vectors. So if we look at this, right, I've got sort of my sphere here, and I've added a point. So if we just want to see this, here's my first point. I'm going to trace a circle. So this point is literally going to use a sine $ff times 5 for the frequency control, and the cosine $ff times 5, 1 in the sine and the cosine. If you map 1, the sine in the y-axis and then the cosine in the z-axis, then you're going to trace a circle basically in that plane, right? So here in the y and z plane, we have a point that is tracing. Cool. In order to sort of test it out, that it doesn't need to be normalized, we can scale up the vector, for instance 1.1, so it's not of unit length. That's just so that later on when we do normalize, we can kind of see the values, right? I'm going to create a line segment out of this. Currently I've got 1 point. I'm going to create a second point. So here I've got a point that is sitting at the origin, and I've got another point. So here's my grid, by the way, right? So we can see it. So here's a point that's sitting at the origin, and here's another target point. So if we merge these two together, we can make a line segment. We can give it a color over here, so it's going to be nice and green, so we can visualize that. Now next, I have an option here to normalize, right? So if I say attribute VOP normalize, it basically takes point number 1, here I've put it into a group, and it is going to make it of unit length. So initially, we started with a point that was a little bit longer, and then make it of unit length. So how does that work? Well, simply grab the position, right, of this point number 1, normalize that position, and output it into the outgoing position. Great. Next, we can say, okay, color this bright green now instead of dark green. So dark green was for the representation of the non-normalized, bright green will be normalized. And so my little switch here allows me to quickly normalize this, visualize it in the viewport. Later on, we will do this inside of a VOP. Okay, great. That's my first vector, or my target vector. Now, what is my base vector? So let's call this one ref target. And now I have a base vector as well. My base vector will basically just lie on the z-axis. So if I transform this point here, or target point, right, to be +1 in the z-axis, we can merge them together, and basically here with an add operation, polygons by group, build another line segment. Great. Let's make this blue so that we kind of sort of stick within the same paradigm. Okay, so this is representing my normal now, and if we merge both of them together, I basically have my two normals, right, behaving as they should. So one is not moving, this is my reference vector, my base vector, my normal, right, and then here we have our target vector. So what can we do now? Well, let's compute the dot product. So how does it work? Well, which are the true vectors, right? Here we sit at the origin. So really the 2 points representing both vectors are going to be point number 1 and point number 3. So as we dive inside of my attribute VOP here, we can basically see the points that I want to bring some information from is point number 3. So we can use a get attribute operation to get to that point number 3, this one. And this will basically represent the normal. So even though I'm bringing in the position, I could have also just computed the normals directly rather than compute it on all 4 of these points. I can compute it on the normals as well. But right now, just for visualizing it, it's easier to visualize it this way. And I can basically bring in point number 3 and also point number 1. So point number 3 is being brought in here, and point number 1 is being brought in here. So notice that I'm using constants to shove this into the lookup value of my get attribute. So here on the first one, I'm grabbing my normal, or rather the point that represents the normal. So that'll be point number 3 as an integer. And on the other one, I'm importing the point that represents my target, which is point number 1. So if we bring both of these together, you can kind of already see that I'm planning to normalize these vectors anyway to make the calculations a little bit easier. But in the scenario that these normals are not the same length, you can actually still compute the dot product, and it'll give you, the dot product value, but it'll take the length as a multiplier into account. Okay, so let's see now this dot product. If we just output it, right, dot result, then we can actually visualize it in the viewport. So if we visualize over here, compute the dot product, I've made a visualizer in the viewport. So we can basically press it over here, dot result, and it will create a visualizer for us in the scene. Now, when you create that visualizer, one of the things to keep into account is what is it? It is going to be a marker over here, and also we need to make it dot result. I've set the text large so that you can kind of sort of read what the dot product value is. Now this dot product value is being computed on every single point. So as we kind of sort of see, we can kind of see the same value here, 0.34, 0.34 there, and 0.34 for every single point. So you could say if you're doing this for like a lot of points, it can get a little wasteful. Maybe you want to just compute it on 2 points with normals instead. You know, it's up to you. Okay, so now that we have this, what can we do with this, right? Well, in a moment, we're going to use some examples and we're going to make some examples. But for right now, let's keep going and let's compute the angle in between. So that arc cosine, right? So remember over here in Krita, we basically now want to apply this bit, right? So we basically want to do that. So let's go compute that angle in between. And in order to do that, right, we are going to take our dot product and we're going to need to do that arc cosine. Now, if we were to say the length over here is not normalized, right, then we need to divide. We need to basically bring that length component to the other side, right? We basically need to take this A and B and divide the other side over here by this A and B length, right? So if we were to take that into account, then here we would take the length of both of these and, you know, have to divide that that dot product by that length. Now, in our case, I don't really care too much about that because we've normalized, or we are about to normalize our components. So let's have a look here. I've got the length now. Let's multiply it and let's divide it. Now notice this is already a little caveat, right? If the length over here of both vectors, right, goes to 0, or one of them goes to 0, then you cannot compute the dot product because you would be doing a division by 0. So you need to have correct vectors coming in. And that's kind of where these normalize operations come from as well, because they will try to at least normalize your vectors before going in. So be aware that there are some scenarios whereby your dot product might error out. And if you're feeding it, you know, garbage in, garbage out, right? So if you're feeding it bad vector data going into it, then you're going to not get the correct data outgoing as well. So a division by 0 could be possible in the scenario that the length of your vectors goes to 0. But let's keep going and let's assume that's not the case. So right now I've got normalized vectors that I'm dealing with, so it'll divide properly by 1. Next is over here a trigonometric function operation. And notice here you can choose all kinds of trigonometric operation. And the one that we are interested in is the arc cosine. So let's pick up the arc cosine. Now, when the arc cosine is computed, we basically get a value back in radians. So what is radians? Radians is just another way to express an angle. Now, if we were to look briefly into Krita and I were to sort of explain how that works, well, basically, whoops, let's make a new layer and let's explain briefly how that works. So here, if I have my trigonometric circle, then we could say, right, here is our initial sort of, you know, vector. Now, our distance along the circle is going to basically be expressed over here. If we were to say, okay, this is of unit length here, then we could say, well, we have this of unit length here. If we were to project that 1 r, right, 1 radian, right, 1 radius onto the circle, then basically it is going to project itself kind of sort of along the unit circle like this. And so, you know, this is going to sort of be projected on this circle. So that basically means that here we have 1 radian. Now, if we kind of keep going, right, then basically here we would have 2 radians. So this would represent 2, this would represent 1. If we kind of keep going here, let's do another one, right? It's not really drawn by proportion properly, but whatever. This would be 3 radians. And then finally, if we go all the way 180 degrees over here, we would end up by 3.14 radian. What else is that? Well, that's pi, right? So basically, if you remember here, this is pi. So if we do this for the entire circle, right, the other side as well, right, we're starting at 0 radian and we're going to end at the full circle, which is 2 pi r. And 2 pi r is the definition of over here your circumference of the circle. So that's kind of where it comes from. Now, if you were to map 0 to 2 pi r, right, you can also map 0 to 360, so 0 to 360 degrees. So we're basically converting from radians to degrees. So what I need to do here is simply convert radians to degrees. Now I could do the math myself, but Houdini already has some nodes for you that will help you with that. So if we do degrees to radian, we can see degrees to radian or radians to degrees. In our case, we want radians to degrees because it's easier. I mean, humans tend to think in degrees, not really in radians. So if we say radians to degrees, right, then we can kind of see the resulting value of this theta, this angle theta, and we can visualize that in the viewport as well. So maybe let's briefly visualize it in the viewport. So I can hover over this. Let's go click theta here and let's visualize that in the viewport. So right now theta is being displayed as a color value. So this is what I was saying. We want to display it as a marker. And then let's color this maybe green so we can see it. And also I'm going to give this a large size. So here we can kind of see, now we can see, okay, the dot product is at 0.9 and my angle is at 25 degrees. Yeah, that looks about 25 degrees. If we kind of keep going, this looks about 40, 45 degrees and so on. So indeed, this is easy to sort of extract the angle in between. Now the problem is we don't necessarily know the direction, right? Whether it's positive or negative, right? Over here, is it negative 35 degrees or is it over here positive 40 degrees? We don't necessarily know whether it's going negative or positive. It just tells us the angle in between the two vectors. So in order to find that out, we have to do some other things with maybe the cross product and figure out if we're positive or negative. We can do that in another video. For now, let's keep going. So with the dot product here, just to sort of visualize things a little bit, there's actually quite a lot of values here, 0.766044. So I'm briefly going to round that. So if we look at the dot result here, in order to round it, I'm going to multiply it by 1000, sort of chop off the remaining fractional data, convert it to an integer as well, and then, or rather, this will convert it to an integer, which will chop off that remaining fractional data into float, and then we can basically divide it back by 0.01, and that gives me basically information accuracy three sort of positions after the period, right? So I'm going to, and that's just for visualizing it in the viewport. And then here I'm going to say dot result rounded string. I'm going to convert that result, right, over here that is coming in using the sprintf function, writing that to a quick little string, result string. And that will allow me to export it here, dot result rounded string, so that I can later on reference that inside of a font operation. Now that's just for visualizing it in the viewport, if ever you want to kind of grab that data and represent it. So here under my font dot, I have a nice sort of representation of that dot product. So let's bring both of them in. So if we look at this here, dot point string, I'm using a point string operation, an expression here is going to reference that dot product value. It's going to be dot result rounded string. Now, if I didn't do that, if I were to just reference the dot result, it would, give me all of these 0, 0, 0, 0, 1, just to sort of represent what Houdini thinks is the best possible way to represent the floating point, and up until the max amount of data that it has. But I just kind of, for visualization, I thought, well, let's just round it there. So that's useful. In terms of visualization, the remaining data over here, okay, so it's just polywired those various, edge segments, right? So all of this. Also, maybe here we've got the drop down. So the drop down starts at, where my target vector is, and it ends at the dot value. So if we look at this for a moment, right? So here, let's get rid of everything except for this point. Here I'm bringing in the dot product operation, so we can kind of reference the dot product from there. And here we're going to build that projected point. So basically I'm after the point that will lie, right, after we project it down here. So where is that, right? Well, we bring in the dot product and we'll simply multiply the position, right, of that base vector times the dot value, and that will lie onto, this sort of z-axis. So from the second input, let's go grab the dot product, the dot result. We can just grab any point. It doesn't really matter because I've computed the dot product for all of the points. And so this will be that projected point. Great. If we merge this together with the target point, and what is the target point? Well, it's going to be ref target, right? So here, basically this vector, and which one am I interested in? It's going to be point number 1. So we are going to keep point number 1, blast point number 0. That gives me my target between sort of 0 and 1, and then I can literally just grab my quick little add operation to create a polygon here and color it, resample it, so we can get rid of every other segment now, just convert it to lines. If we look at this, right, so 0, 1, 2, 3, 4, 5, 6, all these little segments, and we can use a group expression with a modulo operation to grab every other line segment. So over here we say at primnum modulo 2 equals 1, that gives me the odd operations. So if we grab all of these, kind of sort of see 1 is highlighted, 3 is highlighted, 5 and 7 as well, and then we can blast everything else. So now I'm blasting and I'm basically left with all of these other line segments. So it's a nice just visualization point of view, right? So here, polywire all of these. I've also got the one at the base, so that's basically this is the representation, sort of the distance representation of that dot product. So how did we do that? Well, again, we've got a point sitting at the origin. We already have computed our projected point, so we can merge both of them together, make a little polyline segment out of this, color it, and transform it. So here I've just moved it down a little bit so that they're not all stacked on top of each other, but that basically allows me to sort of visualize all of my line segments, polywire this, and I've got a nice sort of representation. Now, obviously, you know, this will work, but it's kind of hard to sort of say, okay, where are we? What are the values? So now let's bring in the values, right? So here, these are my dot product values. Again, the same thing with the expression. Let's go grab our rounded string. I've done the same rounded string for my theta, my angle. And so here we can kind of see the angle now coming in as well. And then lastly, let's just put the annotations in there. So the circle itself, right? So to sort of see, visualize what that unit circle is. And then here I've got the various font operations displaying, you know, the annotation. So we're dealing with the dot product, -1, 0, and 1. Okay, let's bring that forward in Z as well so that we are not interpenetrating with our polywired line segments. And let's bring everything together. And so now I've got a nice, easy visualizer, a nice way to explain how that dot product works. Cool, nice. So maybe let's quickly save the scene and also let's dive into some examples right now. So what could be a nice way to sort of showcase an example here, right? So now we can kind of go into the scene and let's drop down to the test geometry for the rubber toy. And there it is. And so what I want to do is I want to cover this toy with snow, so to speak. Well, basically, what does that mean? I want to identify the vectors that are pointing up in Y. So let's basically get rid of the color. We don't really need the color. I want to basically see all of the normals. So it looks like there's already some normals there. And so what happens if we now visualize the dot product, right, instead of this textural data? So I'm going to throw away the shot material path so that we can see the object just in black and white. And then we can kind of, you know, visualize it with the rainbow again in a moment. So here, the shot material path, if we throw that out, then, you know, we got rid of the shader, or at least the shader assignment. Okay, so next, let's compute the dot product. So let's say compute dot product. So how do we know, now it's actually, how do we use this, right? So over here, I'm going to say, I want to compute the dot product, right? And it is going to be between the normal. And what is my second vector? Well, by default, it's already defined over here as 0, 1, 0. So it's already defined against the y-axis. If I were to promote this parameter so that we can get the sort of custom vector out of that, we can now specify this, you know, as part of our directional vector later on. So I'm going to give that to the user to define. Now, a user might not sort of want to know exactly the values to be normalized. So inside, it might be a good idea to normalize both vectors. So here, I'm going to normalize this one, and I'm also going to normalize the other one. Great. So why do you do this again? Well, so that we're working in that unit circle, so that my dot product values will be neatly defined between +1, 0, and -1. Right? So if we now look at this dot product value, we can shove it directly into the color, but the problem is Houdini is not really able to display negative colors. So you can kind of sort of see that it looks like super black, right? So this bottom portion over here where the values are negative it's super black. So the other thing that we can kind of do briefly is bind export this and call it that dot result. Remember, we still have our dot result here, so that is going to get picked up by my viewport visualization. Oops, I need a bind export bind export, and let's name it the same way. Let's name this thing dot result. So this is going to give me a lot of values in the viewport, right? So you can kind of sort of see over here at the top, right, where the vectors are basically in alignment. So maybe a little hard to tell, but it's basically close to 1, 0.9. Now, where we are perpendicular on the object, so somewhere on the sides, right, it's going to be close to 0. So here we can kind of see as we go from positive 0.3, 0.1, 0.1, 0.06, 0.02, so we're close to 0 over here, and then finally we're going to go negative. So we can kind of start seeing a gradient appear now. You know, gradients, right? I love gradients because we can trigger all kinds of operations with that. So one of the things that we can do is remap this, right? Just so we can see it a little bit better in the viewport, and remap our dot product value, because we know the values are going to go from -1, from -1 to +1. So if we say, okay, you start at -1, go to +1, and I'm going to simply normalize that attribute so that it's nicely mapped 0 to 1. So now you can kind of see there's a gradient that is, you know, white at the top and black at the bottom. Again, just for good measure, might as well just map it through a rainbow ramp so we can kind of see it over here as well. So here, if we map this into the U attribute of that ramp, then we can kind of see, right, it starts over here at 0, red, and then, you know, all the normals at the top are basically going to be this purple, are going to be 1. Yeah. Cool. So what can we do with this now? Well, we could isolate certain areas, right, and scatter points. So for instance, if we were to say, I'm going to make this into a much harsher black and white mask, and then we can kind of use that mask to sort of scatter some points and turn those points into a VDB volume. So here, let's say, I'm going to say dot, and then it's going to be a threshold, right? So we're going to sort of clamp the values at a certain, you know, the certain threshold. So here, dot result, we can bring that dot result in here, dot result, and we can simply do a quick comparison. Now, whether it's a comparison, that means it's a hard if statement, or we can do a fit function, and we're going to have a soft edge. But for right now, let's do it with a hard if statement. So if our dot product is greater than a certain threshold, promote parameter, right here, we can kind of say this is going to be my dot threshold, and let's put that in the label as well. And maybe, sure, let's leave the default at 0 for just a moment, and let's shove that into the color value so we can easily see it inside of the viewport. So, okay, if we now start modifying our threshold, and actually my threshold should be able to go negative, so I'm going to modify my float range so it can go negative to 1. Cool, so now let's have a quick look. So here we can kind of see at 0, so this is where the dot product is perpendicular, right? 0, remember. If we go back briefly to our vector layers here, let's hide all of this. Let's also hide that group, and let's revisualize the other one here. So if my dot product is projected perpendicular, we are at 0. So we're playing with that threshold as it goes between -1 to 0 to 1. So this allows me to select only the utmost top points. So basically, if we say 0.7 over here, right, we can kind of sort of see it's going to select only that top layer. Now, the next step could be I could use this scatter operation and scatter only onto those polygons. So instead here, right now it's scattering everywhere, but we can say, show me only the points with the density attribute. Now, we don't have something named density, but we do have something named CD, the color value, the diffuse color. So here now you can kind of sort of see it is scattered indeed everywhere where it is, you know, sort of white. Now we can turn on the Pscale value over here as an export as well, Pscale, and that's going to be useful when we do VDB from particles. So VDB from particles. And when we do this, I can basically start building my value. Now this Pscale, so why do we not see anything? It's complaining because this Pscale is probably too small. So I'm going to say, let's showcase 01. So it needs to be a little smaller over here. Okay, we're starting to get to these particles. I'm not 100% sure if I want the Pscale over here on the outside. Maybe later on it might be nice to sort of blend this down a little bit. And then we can VDB smoothen this as well. So VDB smooth the SDF. And let's have a look. All right, so it's a little tiny over here, so we can definitely sort of crank up the radius a little bit and fill this out, right? Now, some of these points, these edge points, not so useful. So maybe let's turn off the Pscale over here, and then we can control the Pscale ourselves. So I'm going to turn the Pscale off, and instead, let's make a quick attribute wrangle. And let's say float at Pscale equals channel function mult something with our Pscale, so something along the lines of Pscale mult. There we go, right? And Pscale. There we go. And let's make that parameter. And now let's set that to something small, like something like 0.01, right? So that we kind of sort of match what we have here with our voxel size. Okay, so it's still too small. Let's make our Pscale a little bit bigger. So something along these lines. So now we have a nice little uniform selection criteria. Now, this could be, if we were to merge this back in with our original object, this could be a very quick way. I mean, this is very rough, this needs refinement, but this could be a very quick way to make some object being covered with snow. So now we have like, you know, a little object covered with snow. Now it's not really realistic snow, because now I'm going to show you some of the drawbacks of the dot product in case you wanted to use this for this kind of example. Now, this sort of looks maybe doable, maybe somewhat acceptable, but the problem is that what if we have a second sort of, you know, test geometry object here? What if I were to say, let's transform this object, right, all the way at the top over here, right? And I'm going to simply say, let's merge in another one. So I'm going to move it down a little bit. So here we can kind of sort of move it down, right? And so, you know, if you were to actually make snow, right, then you would think, well, one object is going to occlude another object, right? So let's move it down a little bit more. But the problem is the dot product doesn't know that there is another object. It simply does a comparison between the normals. It doesn't take into account that there are actually two objects. So basically, we're going to have two, you know, bits of snow over here sort of scattered on top of each other, because again, our mask doesn't care. So it doesn't know that, oh, maybe this object is actually occluding the other one. So if you wanted to do that, then you might want to use a different algorithm to compute this. You might want to try to do, if it's specifically for snow, you might want to sort of put a grid over here with some points and then ray all of those points down, right? I mean, if we very quickly were to do this, let's make a quick match size, or we can put just a grid on top. Let's maybe do that. Let's put a quick little grid on top and transform it so that it sits above these objects. And that's just sort of an example on how to basically get around that limitation that the dot product is doing, right? So if we scale it down a little bit, right, so something like this. And we can scatter some points on this as well, and we're going to need to give them a downwards projection direction, right? Now, probably we're going to need a bunch more points, and let's do a ray operation. So we are now going to ray this down onto our target geometry. So this is our target geometry, and if we say project ray, we can say by normal, by vector, I want to show my vector, and I'm going to break this little expression and just set this to -1. So now we can kind of see, all right, it is projecting downwards, and some of the points have hit, but a lot of points have not been hit. So if we simply say, okay, give me the group, create a point group over here, the ray hit group, then we can blast everything except for those points that have been projected downwards. And ray those. So here, ray hit group, and say, I want to delete everything else. And we're dealing with points. And so now basically, right, we can kind of see that, it looks like, you know, nothing got hit on the other one. Well, no, because it completely got occluded. So you can kind of sort of see dot product's useful, but sometimes you have to do a ray hit operation. So now if we were to switch this sort of set of points over here, just kind of after we've dealt with the scatter, right, we can basically switch to now our projected points. And let's have a look at our output now. So now we can see that indeed the top one is occluding everything else, right? So that's basically what the ray hit kind of allows us to do, versus the dot product over here that doesn't take that into account and literally does a normal computation. Now, why would you want to do that? Well, the ray operation is much more expensive, computationally expensive. So if you're dealing with just one object and it's not really self-occluding or, you know, all that, because self-occlusion can also be an issue. Like for instance, if we were to say this grid, this normal that we're casting, right? Currently we're casting it down, but if we also were to cast it a little bit in negative 0.1 right here, then my normals are basically going to go ever so slightly to the side. So now it's as if these points are being projected to the side. So we are going to hit both objects. Right, but again, it's still pretty cool because, you know, over here it's like a little roof, right? So my rain or my snow or whatever is basically blocking the other side from, you know, doing what it needs to do, in the sense that there shouldn't be any snow here. So the ray operation, nice operation, but more expensive to compute. So, you know, use with caution. So let's save this again. Another useful one to just sort of be aware of, right? Instead of building it ourselves, right? Especially, I mean, if you're dealing with just this sort of black and white visualization with a hard threshold here, as we are doing, then there's another useful operation to be aware of, and that is the group operation. So if we were to say, let's group these points, right? And notice right now, we're back to our original sort of, it's grouping everything. I want to say group the points, and we can enable here group by normals. And then we can say specify the direction. So if we set our direction to +1, and then we can specify sort of how much we want to group. Does this look familiar, this operation? Well, it should, because if we say spread angle 90 degrees, you can kind of see it is taking it up to sort of the perpendicular 90 degrees against that y up value. Now you should start to understand what operation is being used under the hood here, and it is the dot product. So keep by normals uses the dot product is just kind of turned into a nice little user-friendly operation for you if you need to have a hard selection. Now, where might this be useful? Well, if you wanted to say, what if my camera is maybe pointing this way? Keep all of the faces that are facing the camera, and let's throw away all the faces that are not. So that's backface culling. So that actually uses that as well. And it uses the dot product against the backside of your object, against those normals that are facing away. Cool, so that's quite useful there to potentially, you know, do something, or here it already says backface from another object if you've got a camera or another object. So that could be useful as well to very quickly select the same deal, right? So basically we blast everything except for those points that were inside of that group. So currently it's called group 1. Let's call this group, I don't know, dot normal or something like that, because basically that's what we're using. And now if we blast everything else, group dot normal, delete non-selected, we're dealing with points, then we will basically end up with sort of that same you know, selection, same as what we did with our own dot product calculation. So again, you know, quite useful. Can be useful for other things as well. Yeah, I mean, if you do that some direction, it's kind of nice to sort of remap that and visualize that as well. So here our dot threshold that we had, right? If we want to make that fuzzy with a fit function instead, we can do that too. So here this dot threshold, instead of doing it with a threshold, what if we simply sort of visualize the dot a little bit and sort of say, if I wanted to say any object now, I can create a dot product. So let's maybe do the entire thing just one last time. And this time I'm going to represent it maybe with sort of where the sunlight is in the scene. So the sun is going to be represented over here with a sphere. It is a primitive sphere. Notice that a primitive sphere has a point at the middle, and it is this point that we're going to use to compare our direction vectors against. So that's going to be quite nice to visualize and to then say, okay, emit, I don't know, particles wherever there is light from this object. So if we say, I don't actually, well, the dot product result here, we kind of want to use the other one. I'm going to say instead, let's use the one that we used for the attribute valve that we used for computing that dot product. And so in the second input, I want to put this transform. So let's move it in the scene somewhere that makes sense. So here we have our dot product value, and let's visualize it. So in order to do that, let's compute that dot product against our second input. So here, get attribute, right, from the second input is just going to be that 1 point number over here, right? And what do we want from it? We want the position. Now, which position or which vectors are we comparing here? Because it's no longer just a symbol up vector, it's against the normal. I mean, it is against the normal, but not so much this one. So what we need to do is we need to compute the difference vector between each point and this target point. So this is going to be our target point. So that's going to go first, and then we're going to start with our point of our geometry. Now, if we were to look at this in the viewport briefly, just to sort of see what this looks like, we can visualize this into our normal. Let's bring back our normals, right? Then we can kind of sort of see all these normals are basically pointing towards that target sphere. So let's see that target sphere, right? And let's see our normals. So here we can kind of see all these normals are pointing towards that target sphere. If I move this around, it's going to be kind of like a nice little control. Also, let's make it a little smaller so it's a little bit less, obvious, or like it's a bit less intrusive. So here we can kind of see all these normals are now kind of nicely pointing towards my target object. Cool. So now if we compare the surface normal against this newly computed normal, we are going to get that difference. All right, so let's have a look. So here, if we say, instead of using this custom normal that we originally created, we can kind of, use our other normal. We can get rid of this one. And let's visualize this in the viewport. So again, I've got my dot result. And so here, now it's against a custom. It crashed. That's unfortunate. Let's see if I can restore. I'm going to pause just for a second. Alrighty, and we're back. So basically, occasionally, unfortunately, when you swap between full screen in VOPs and also trying to display things in the viewport, it can happen that the scene crashes. It's random. I don't know why that sometimes happens, but make sure to save often, right? So we were basically looking at displaying the color value over here of the newly calculated dot product, right? So we're basically grabbing our dot product, subtracting our vector, and computing it against our surface normals. So that gives me the dot value. This is currently refitted -1 to 1, 0 to 1 here, and the pure dot product value will be stored in my dot results. So let's go into our scene now, and let's have a look as I turn my values off. So now we can kind of see as I move my sphere around, and here we can basically sort of see, okay, cool. It is basically showing me every portion where the object is illuminated. And again, if we wanted to grab our threshold or our scattering operation, we can just continue and duplicate that portion of the network. And here, now I can kind of very quickly control where to scatter all of these points. So again, right, it's quite nice to sort of be able to say, okay, the front of the object, or the top of the object, or the back side of the object, and so on, right? So, and this can be totally animated, so you can emit particles from this and control it that way. So it's quite a useful operation to quickly use for an emitter or some threshold, yeah? So there's also some field of view calculations, but maybe we'll keep that for another class, specifically like for field of view of agents and flocking, where we're basically going to compare the current direction vector of the point or the agent against its neighbors, and then we can kind of, with a field of view, sort of what does the agent see in its field of view. And that would be the dot product as well. And then we can kind of find the neighbor that is has the highest dot product value in its field of view, and do something with that, like avoid it or be attracted to it. So maybe in a future class we'll do, or in a future tutorial, we'll do a little flocking system and use the dot product in that way. So with that, that's kind of what I wanted to cover today. Hopefully this has been useful to you. If you do like this kind of content, please do like and subscribe, and smash that notification bell so that every time I post a video, you will get notified. Thank you so much. See you in the next video. Bye.